Hi everyone, so I'm back again. Since the last video was really long, I'm gonna try to make this short, but I don't know how long it's gonna go. I do promise you that the video is gonna be interesting. I'm gonna prove my point that the front of center is not directly correlated with its trajectory using probably two methods, and they're gonna be really interesting. So what inspired this video was because in my previous video, there is a commenter, a viewer, that gave some really... I first have to apologize that I think those comments are so stupid. Those arguments are so ridiculously stupid. So you see, sometimes we don't have to prove something by actually doing it. We can use correlation to prove something. So for example, we don't have to push someone off a plane without a parachute just to prove that falling off a high place can lead to death, right? We just have to prove that a certain amount of G's or impact can cause fatal injury, and falling off the plane without your parachute can induce very high G's that's exceeding the fatal limit, and that is sufficient to prove that falling off a plane without a parachute is a bad idea, right? I don't have to push someone off the plane just to prove my point. And the previous video actually, if you know some basic physics, like maybe I think high school level physics is actually sufficient. You should be able to follow through and understand that I use existing established physics, and as long as I do not have any pitfall in between, then it is proven. It literally is proven as long as I do not have any pitfall in between, because I use what has been established and proven, and I relate it to my conclusion. So unless you can prove that there is a pitfall in between, otherwise my verdict, my conclusion holds true. But of course, for people who has not studied science, they don't understand that we can do that. Every time a scientist proves something, they don't have to prove everything from the beginning of time and prove every single equation they use. They don't have to do that. They just use something that is proven, established, and as long as that law, that physics law, is used correctly in the correct context, all the conditions are correct, and then a conclusion that is drawn from that application would be valid. Okay, so I'm gonna first go back to my original conclusion, because he said there is no conclusion. Okay, things like this is actually considered a conclusion in science. We have a condition and we have an effect, right? Is it called an effect? I forgot. So basically, there's a certain condition for whatever that is going to come to be valid. All right. So if the initial condition is invalid, then whatever is behind is not applicable. Okay. But I'm gonna word it a little bit differently, same meaning, but I think this probably will create less confusion, although there is actually no confusion in the previous video. So I'm gonna read it out. I think my words are a little bit small this time. It's difficult to write. Alright, so here I'm gonna read. In the absence of external forces, such as wind, if two arrows with identical mass, velocity, drag, friction, and initial position, such that they only vary by their front of center, provided that the front of center produces sufficient leverage to stabilize the flight, such that drag and friction remains unaffected, then the trajectory of both arrows are identical. Hence, front of center is not directly correlated with an arrow's trajectory. Okay, so let me go into the details of what I'm trying to say here, because it's very long right here. Okay, so what I'm saying, first of all, the condition is that in the absence of external forces such as wind, because if you have wind, it's an external force that's pushing your arrow, and you're gonna get random results depending on the randomness of the wind direction. So we always have to remove external force, otherwise whatever result we have is caused by the wind, it's not caused by the front of center. We are trying to investigate only the effect of front of center. What does the front of center contributes towards the trajectory? We want only the front of center and nothing else. So we already remove wind as a factor by definition. So if two arrows with identical mass and velocity, so why I use velocity here is because velocity is both speed and direction. Okay, speed and direction. Drag and friction is actually not the same. See, drag has to do with the turbulence of the air around the arrow as it flies through, as it pushes the air around, and friction is the air molecules rubbing on the surface of the arrow. So drag and friction and initial position. So why I mentioned this one, because if you start at two different environments and you shoot two different arrows, if you have different environment, for example, different air density, you can have a different result. So we want to start with the same initial position and same velocity, meaning they're going to be shot at the same speed, at the same direction. Both of these arrows are going to go through the same environment. Okay, with all those being identical, pretty much everything must be a constant, so that we know that the only variable is the front of center. And whatever result that we get is due to the change in front of center and not anything else. Alright, then the second condition here, now the front of center has to provide sufficient leverage. And why do I say that? I didn't provide an exact number of front of center. I didn't say like, okay, 5% or 10%. I didn't say any exact number. Why is it like that? If you have a high front of center, you can use a smaller fletch to get the same leverage. If you have a low front of center, you need a bigger fletch to get the same leverage. Therefore, the front of center that is considered sufficient will differ depending on your fletch being smaller or bigger. Okay, so that's why, provided that the front of center produce sufficient leverage to stabilize the flight such that drag and friction remains unaffected. When I say unaffected, I mean that the arrow has to minimize its drag and friction and goes into the wind. Okay, and not flying face flat towards the direction in which it is going. All right. So as long as the arrow is pointing into its path, then drag and friction is unaffected. Okay, with all that condition being true, then the trajectory of both arrows are identical. Okay, that's what I meant. Okay, so all of this has to be true for this to be true. And because of this, what we can see is the front of center is not directly correlated with the trajectory, because otherwise different front of center will have directly result in different trajectory. But now we have a case of different front of center may not result in different trajectory. Therefore, front of center is not directly correlated to its trajectory. Okay? And I also explained that in the case of the flight artery, a flight arrow, actually what happens is this portion here, the condition here, is invalidated because the front of center does not provide sufficient leverage, and therefore it cannot stabilize the arrow in flight. Therefore, drag and friction is actually different. So it invalidated this condition, and therefore this conclusion here is not invalidated, but is not applicable. The condition is not valid. Therefore, whatever conclusion I draw is not applicable in the case of flight artery, and therefore flight artery do produce a different result if you have the front of center being very, very close to the center of pressure, which I explained in the previous video. Please watch that. Okay, so with that gone, I'm gonna go through the stupid argument, the really, really ridiculous stupid argument. So the argument that he has was what's it called? Okay, whatever. So he says that a higher front of center requires a heavy point. You need to have the heavy point to get the higher front of center, which leads to a higher mass and therefore a weakened arrow spine and hence the arrow nosedive. Okay, that is what he stubbornly just keeps repeating, that the higher front of center must have a heavier point and it's gonna nosedive. And he keep asking me to prove my point and that his is not true. So I asked him what kind of proof he is using, and the source that he is using, he says, is a public consensus found on the internet. Right? His source is the public consensus that he finds on the internet, which claims this: a higher front of center improves stability but loss of trajectory, which means nose diving, while a lower front of center is less forgiving or unforgiving, but a flatter trajectory, which means a greater range. I may not have worded the way that he said it exactly because he deleted the comment. However, I know where he's coming from. I know because big companies that sell arrows, big companies, you should be really ashamed of yourself. You should be really ashamed of yourself that it takes me to prove you wrong. You can search this, okay, and you will find those companies that I mentioned. And this is absolutely not true. Okay, big companies, international companies, giving you stupid things like this. And therefore the public consensus. This is actually not true. I'm going to prove that. But first of all, let's first agree that what they mean here is a higher front of center will actually improve your stability. Well, we agree with this part. But he said it's going to cause a loss of trajectory. What do you mean by a loss of trajectory? Which is what they call as nosediving, meaning that the arrow has a shorter distance, a shorter range, right? That's what they mean, because we have to be in the same context. So what they mean here by the loss of trajectory is a loss of distance. Instead of going further, it has dropped earlier. The range is shorter. Whereas when they say a flatter trajectory, they mean going further. Because how do you make something flatter, right? Because gravity is always pulling things down. The only way it can so-called flatter, and that's what most people understand, flatter trajectory means it goes further, greater range. Okay, this actually comes from a pitfall that says heavier objects fall faster than lighter objects. Okay, I say again, heavier objects fall faster than lighter objects. Now, if you have been to primary school and high school, I believe you already know what the problem is, because this is not true. This is not true. I'm not gonna prove it here, but what you can do, you just take a eraser, a small eraser, and you take a steel ball or whatever really heavy object, or maybe even like a bottle of water, big heavy bottle of water, small eraser. We have a huge difference in mass. One like this one here is really heavy, like more than a kilo, and a small eraser will be a couple of grams. Drop them simultaneously from a great height into the ground, and you will see that they will both hit the ground at the same time. So the lighter object is not dropping any slower. Okay? Yes, some people may argue that, but the feather will drop slower. The feather is actually a different case. The feather drops slower because of something called terminal velocity, which is affected by the air drag, the air resistance. So if you were to drop a hammer and a feather in an environment without air drag, for example the moon, and you can search this on YouTube, just search it, NASA, whatever, they have done an experiment back in, I believe, 1970, where they dropped a hammer and a feather on the surface of the moon, and you can see them hitting the ground at the same time. Because without drag, without air resistance, then nothing is going to stop the feather from falling naturally towards the ground at the gravitational acceleration of the moon. So anyway, this one here, I don't actually have to prove this because this is really known. Okay, you can do your own experiment, and you can also watch YouTube videos about this, which is what I just mentioned. They actually prove even on the surface of the earth in a huge, there's a video where they drop a bowling ball and a feather in a huge vacuum, I don't know, vacuum something chamber, huge vacuum chamber from a great height. And you can see that the bowling ball and the feather drop at the same pace, the same acceleration downwards, and they hit the ground at the same time. So it is drag. Air drag is what making the difference. Okay, so this one here is false. Okay, I hope I don't have to repeat this again. Okay, just YouTube it or do your own experiment. This is super easy to do. Next, I'm gonna prove this one here. I'm gonna include a video. Alright, so now I'm going to disprove the claim that you need a higher point weight to get a higher front of center, and that leads to a heavier arrow and slower, so it nosedives. And to disprove that, I have over here 2 arrows that has been balanced on this little box here. It doesn't take a genius to tell which one has the lower front of center, which is the one that is further from me over here, and the one that has higher front of center, which is the one closer to me over here. Now, you'll be surprised that both of these points are identical in weight. 165 grain point over there, 165 grain point over here. I know because I literally designed these points. Okay, so I know these points. They are 165 on both of them. All right. Even though they both have the same point weight, they have different front of center. Okay, and in fact, this one here with the lower front of center is heavier at 34 grams, whereas the higher front of center is lighter at 24 grams. That's a huge 10 gram in difference. Okay, 10 gram difference is a lot, and yet you see this one has a higher front of center and it's actually lighter. So higher front of center does not lead to heavier mass. In fact, it depends on the shaft weight. It really depends on the shaft weight because most of your arrow weight comes from the shaft and not the point. So by keeping the same point weight, but I save the weight on the shaft by using a lighter GPI, a lower GPI shaft weight. And there you have. We get a higher front of center and actually it's lighter. Okay, so we just disproved this. Now I'm going to actually prove this one here using something called logic. Logic as in mathematical logic, not common sense logic, all right? It's not common sense because common sense not necessarily making sense. For example, if you're hungry, eat something, right? That's common sense. If you're homeless, buy a house. Sounds right, but it makes no sense. Okay, it's not common sense. So common sense does not equal logic. I'm talking about logic. I'm not talking about common sense. All right, I'm gonna disprove this one using a method where we call proof by contradiction. So first of all, we're gonna assume the claim is true. We assume that what they say here is true. We want to believe this. We want to believe that this is true. And we believe it. Okay, we believe it. The claim is a higher front of center result in a shorter range. Right? Because this is the only condition that it says. A higher front of center improves stability but it causes a loss of trajectory. So a higher front of center, shorter range. Alright. So we're gonna do this experiment on the moon. Okay, just imagine we go to the moon to do this experiment. We're gonna ask a handsome astronaut here, this cute guy here, to do our test on the surface of the moon. Well, some of you might think that, oh, why do we go to the moon? Well, it just makes the entire argument a lot easier. We could do it the same argument on Earth, but then the equation becomes extremely complicated. We have to talk about both the drag and the friction. But in the end, all the calculations result in exactly the same thing. So we might as well just talk about the surface of the moon. So now, if this is true, if this is a true law, physics law, in which it is applicable universally, okay, if this is true and can be applicable universally, then it will also be true on the surface of the moon. You can't say that, it doesn't work on the moon. It must work on the moon if this is true, okay? So we assume that we're gonna have this astronaut shoot our bow and arrow, our arrow, and because we want to go for the maximum trajectory, the maximum distance, we ask him to shoot at a 45 degree. Just assume he has so much skill he can do that. Okay, 45 degree. And whatever speed that he shoots the arrow, we call it v, as in velocity, v. Okay, surface of the moon. So the distance here, because on the moon the atmosphere is extremely thin or no atmosphere, so the range of this arrow is velocity squared divided by gravitational acceleration of the moon. Okay, I do not have to prove this. Okay, I do not have to prove this. You can search on Google, Wikipedia, projectile motion. You will find this formula. It is an established formula proven by scientists and physicists for hundreds of years. So I do not have to prove this. Okay, I do not have to prove this. It has been proven already. Now, whatever distance I get, okay, now I decided that, hey, I'm shooting a bit too far. I actually want to shoot a bit nearer. I'm willing to sacrifice the range for a better stability of the arrow. Okay, I want the arrow to be more stable. I'm willing to sacrifice some distance. So I'm gonna cut my arrow half an inch shorter. So when I cut the arrow half an inch shorter, what I did is I reduced the shaft weight, right? I cut it half an inch shorter, I reduced the shaft weight by a little bit. This actually results in, since the shaft is lighter, the point is the same weight, we actually have a higher front of center. Although it comes at a reduction in total mass, which I just showed you in my another video just now. Okay, I'm gonna have a lower mass, but I'm gonna have an increased front of center, even though I'm still maintaining the same point weight. Okay, but then now, because I have a lower arrow mass, it shoots at a higher velocity, right? Lighter arrow shoots faster, and I don't have to prove that as well, because if you look at the kinetic energy of an arrow, or just kinetic energy of a projectile, if we have the same energy that we put into the arrow, then as the mass of the projectile decrease, velocity increase. As the mass increase, the velocity decrease. That is a proven. Again, it's proven. I didn't do it. Okay? I didn't do it. Scientists and physicists proved it. Okay, I just used them. Okay, so a lower mass increases the arrow velocity. And now the new range is, since this has increased and gravitational acceleration didn't change, what's going to happen? My range has increased, but I increased my front of center because I want to decrease my range. But now I actually have a case where my range increased. That shows that this assumption here is false. Therefore, this is false. Okay? Now, I'm going to do the other part. Now, supposingly, I assume that this is still true, and they claim that a lower front of center increases the range. Okay, so we're gonna have the same guy doing the same thing here, but after the first shot, I decided that, hey, you know what? I want to shoot further, and I don't think we need as much of a FOC for it to be stable enough. Let's sacrifice a little bit of FOC. Let's go for a greater range. So what I'm gonna do, I'm gonna switch the shaft half an inch longer. I'm gonna use the same point, but I'm gonna shift to a longer and slightly heavier shaft. It's half an inch longer. So the shaft is now heavier, which reduces the front of center. And it also increases the total mass of the arrow. Since it's heavier, the arrow is heavier, it decreases the velocity, and our new range, what happens? Our velocity decreases, but our range also decreased. But if this is true, it will have increased the range, so therefore this is false. Okay. Now next one. Supposingly you claim that this thing only works on Earth, but not anywhere else in the universe, then this is also not a physics law. Okay. Now suppose you claim that it can only work with an existence of air. Okay, air drag, then you just proved my verdict and conclusion is true. It's all about drag, air drag. And let's look at the formula of drag. The air drag is half the density of air times the velocity of the arrow squared. Now this part is actually the interesting part. The coefficient of drag and the area, surface area that's causing the drag. Now let me explain what this is. But okay, so let's go through the entire formula, right? Half is a constant, we don't have to worry about that. Density of the air. This is exactly why I mentioned velocity and initial position, because if you start at different position and different direction, you may not go through the same air density, and therefore result in different drag and friction. Okay, so we want to make sure that we have this air density being a non-factor, okay, being a constant. Velocity, well, by definition, we have to start with the same velocity. Okay, so don't argue with me that the heavier arrow is gonna be slower, because by definition, we need the arrows to have the same velocity. So if you have a heavier arrow, you have to use a more powerful bow to have both of them travel at the same speed. We want the same velocity. I don't care about the mass. Look at the formula, it has no mass. Mass is not in there. It's unrelated to the mass. Okay, drag does not have any correlation with the mass. Okay, coefficient of drag. Now, coefficient of drag is actually what I mentioned before. Although I don't think I specifically mentioned it very precisely. So, coefficient of drag is what the air sees as it goes through the air. So, I'm going to try to align. So, if it goes through the air like this, because the arrow is stable, it has enough leverage, it's stable, it goes through the air, into the air like that, then all you see is this. For a 4 fletch, for a 3 fletch. Okay, sometimes we call this a bullet hole. Okay, so if your arrow is not dancing like this, right, then this is all you see. Meaning this is gonna be a constant. Unless your arrow is doing this. And in the case of the flight arrow, it is falling face flat into the air like this. Okay, so instead of like that, it is falling face flat with the fletch here and the point here, like this. Okay, in case it looks very vulgar, let me just remove this. Unintentionally, okay, unintentionally. The area here refers to the okay, the same drawing just now. I'm going to draw bigger. Okay, I'm going to draw bigger. The area refers to here, the shaded area here. How much surface is exposed, pushing the air out. So that is what it meant by the area here. And you will notice that in this formula, front of center plays no role. The mass of the arrow plays no role. And I didn't invent this, okay? Scientists and physicists gave us this. It's proven, okay? It's proven, it's established, and the formula does not have mass and front of center because they don't matter. They don't matter, they do not influence air drag, okay? So, at this point, I think it's sufficient to prove this without doing an experiment. But I will still actually do a real experiment because I think it's quite interesting. I'm gonna literally drop arrows from very high just to show you. Alright, so before I actually drop any arrows from the 3rd floor down to the 1st floor, I'm gonna first have to explain what I'm doing. The test I'm gonna do is actually related to the topic we're in. Otherwise, what's the point of doing a test which is unrelated, right? So this case, let's talk about an imaginary case where we're going to shoot on the surface of the moon. Again, the same handsome astronaut here, shooting the arrow at 45 degrees for the maximum trajectory given by this formula here. And the height is actually given this. Again, I didn't create this formula, okay? Alright, so what I will be doing is I'm going to prove this half here. Okay, I'm not going to prove this half here. Why? Because by definition, you want to shoot the arrows with varying front of center, different front of center, but they will have the same mass, same velocity, okay, and same angle from the same initial position. They'll be shot out, and because drag and friction, air drag and friction will be the same, okay, for both of these arrows, or arrows, a lot of arrows of varying front of center, then you actually get the peak point here being the same, okay, and that's because purely because the conservation of energy, the law of conservation of energy, as they climb in height, they lose the kinetic energy and convert it into potential energy, gravitational potential energy, which they regain as they come down. So this part here will be the same, will be consistent for regardless of your front of center or mass. In fact, actually the arrow mass don't even matter. The arrow mass will not matter and the front of center will not matter. What only matters is the height here, you see, depends only on the velocity that it starts with. So of course, if you were to do this on the surface of the Earth, because we have air drag, you lose a little bit of height here. You actually lose a little bit because of drag. But we just show you that drag has nothing to do with arrow mass and nothing to do with the front of center. So just by those formula alone, we know that actually it's going to reach the same point. But of course, if you still want to prove this one, you may as well just do your own test and experiment. Okay, so I'm going to prove this half here. And the way I'm going to be doing this half here, first of all, I'm going to claim this. As the arrow passes this point, okay, the moment it passes this point, I'm going to drop another arrow, okay, another arrow from the same height, in this orientation. Since the arrow will be coming in like this, right, I'm going to drop it in this orientation. Now, actually, if we were to really be doing this on the surface of the moon, the arrow is going to go like this. It's going to go initially like that. At this point, it's going to be like this. And as it hits the ground, it's going to be like this. Okay? It's not going to rotate because there's no drag, there's no friction, meaning there is nothing that's going to push against the tail. It's not going to correct itself. It's going to just fly like this and land like this. Okay? That is what's going to actually happen on the surface of the moon. And that proves to you that the front of center has nothing to do with this. The front of center has nothing to do with the trajectory because the entire arrow start like that and land like this. Okay, so but of course, since it's just to make things easy for you to understand because somehow we have to relate back to Earth, right? So as it passes this point here, we're gonna drop the arrow from the same height. And my claim is this. Actually, well, I don't really claim this. It's proven fact. I'm just telling you. So the arrow that you drop from there and the arrow that just passes at the same height, although it has a forward velocity, both of these will hit the ground at the same time. Both of them will hit the ground at the same time, but because one has a forward velocity, it will travel further out when they hit the ground together. Okay. This one, again, I don't have to prove this. I think you have done this kind of experiment and test in primary school or high school, where if you were to drop two balls from the table to the ground, one of which has a forward motion, the other one is maybe has a slower motion, you'll find that both of them, as they roll off the table together, they will hit the ground together, but the one with a greater initial velocity will travel further. Okay, so the amount of time it takes to hit the ground is how much time it can travel forward before it stops. Okay, understand this point? So we only need to prove that the arrow, when I drop it, will hit the ground at the same time, regardless of the front of center. Regardless of the front of center, it will drop at the same pace. What else? Now, some of you may argue that the arrow that has a higher velocity forward will drop slower, and I can tell you that this is impossible. Okay, the one that has a velocity forward will not directly cause the arrow to drop slower, and I can prove it using a paradox. First, let me remove this one. But anyway, this experiment is actually a known experiment, has been done probably for several hundred years. So I don't think I should waste my time doing that. All right, so let's say as the arrow passes here, you drop another arrow. Okay, drop another arrow. So let's say we have three guys here, three passerbys. So this guy here just stands there doing nothing. Okay, and the other two are actually moving in this direction at this speed, half of the arrow speed, and the other one is moving at the arrow speed. So what do they see? This guy sees this one arrow is going forward and coming down. Okay, this arc right here, whereas the other arrow is coming straight down. Okay, this guy sees that two arrows, one going back and one going front, both at half of this speed, right? Because he's going half the speed, so this relative to him, this arrow is only moving at half of v1. Whereas the other arrow that you drop straight down, he sees as moving backwards at negative v1 because it is on the other direction. Okay, it's going the other direction at half of v1. Okay, and this guy here, he's gonna, because he's moving at the same speed as this one, he's gonna see this arrow, the one that is actually arcing, he's gonna see it dropping straight down without forward motion. Whereas he's gonna see the arrow that you drop straight down to actually be moving backwards, meaning negative v1. Alright. And if you say that the one that is moving forward drops slower, okay, then you will have a paradox, because this guy says this one drops slower, this guy says they both drop at the same time, and this guy says that one drops slower. So we cannot have this paradox. Okay, there's only one reality. All of these guys live in the same reality, same reference frame. So of course, unless we're talking about speed of light, but you know, that's not what we're talking about here. So for R3 kind of velocity, not the speed of light, okay, then the paradox does not occur. All three of these will agree that the arrows hit the ground at the same time, which is why the experiment is relatable, even though I just drop it from the sky, right, just from a certain height down, it is relatable because the amount of time it hits the ground is the same as this guy traveling here. Okay, so let's do the test. Okay, so these are the arrows that I'll be dropping. So just now I mentioned that I'm gonna drop arrows, but I didn't mention what arrows, right? So the thing is, gravity affects them all the same. So as long as drag don't play a role, then it's no problem. So in these cases, even though they all have different front of center, in fact, they even have different mass. This one we weighted just now, 34 grams. It actually has a very low front of center. This one is a little bit better in front of center. The point here is 185 grains, 185, this one 165 grains. This one weighs 26 gram. That one weighs 24 gram. This one has 190. Okay, this one here, a different fletch. This one here is not the same arrow as the previous one. This one has a 190 grain point, heavier than the 165 one. This one has a massive 340 grain point, and this weighs 47 gram. So we have 4 different arrows to drop from the 3rd floor down to the 1st. And because they all have enough front of center, okay, enough. They have good amount of fletching. You can see 4 fletch, they all have good enough fletching. So even though we have varying amount of front of center here, but the leverage that we have is sufficient to stabilize the arrow as they fall. So when they fall like this, and they rotate and point into the path of travel, they will have reduced drag. So this would be different from the case of a flight arrow, where we have, in the case of flight arrow, we have negative front of center, and the center of pressure is pretty much near the center of gravity, the front of center part, and as a result, as it falls, it cannot rotate. So if it doesn't rotate, then what happens is it's going to fall face flat, and there's a lot of drag on the entire shaft. But not with this case. You see, they all have fall of center. They are all past the middle. All of them are past the middle. Even though some of them are smaller, some of them are greater, but they're all past the middle, and we have enough leverage. So when I drop them all, you will see that they're going to impact on the ground the same time. Okay, I haven't do it yet, but I know the result, which I'm going to show you later. They're going to hit the ground at the same time. But because I have 2 hands, I'm going to drop 2 at the same time instead of having 4. I can't hold all 4, and we're going to have like arrows colliding with each other if we try to let go of 4 of them. So I probably will pick 2, and then the other 2, and after that I'm going to match, like, let's say for example, maybe these 2, then maybe these 2, and then I'm going to put these 2 together. So at least 3 tests. Alright, so this is the 1st floor where I put this mat here so that I do not hit the ground and damage the floor. And I'll be dropping arrows from, I'm not sure if you can see it. Okay, I'm gonna point it there, right? It's pretty high. Okay, so this is where I'll be dropping the arrows from. Alright, oh, it's pretty high, all the way down. And I can assure you that for target archery and hunting, your arrow is not gonna arc big enough to reach this height. So for target archery and hunting purposes, this is good enough proof. Alright, this is good enough proof, but I do not have someone else to hold the camera, and I only have one. So I'll be putting this camera on the ground floor with a tripod to record as the arrow impact. But I'm gonna show you how I'm gonna drop them first. As I drop them, I'll be placing them horizontally like this. Okay, I'm gonna make sure that the point is on the same level, horizontal like that, and then drop them together. And the reason is because if yesterday I tried it, if I do it this way, as it corrects in flight, as it corrects, they tend to hit each other. So I'm going to prevent that by putting it this way. Also, If I were to drop straight down like this, you might say it is irrelevant because it is cutting through the air straight away, right? So we intentionally do it this way so that there is some air resistance pushing against the belly, and it takes time for this fletch to correct itself, to straighten and go down. Right, so these are the tests that I can do with very limited amount of resource. If you want better result, or you want to disprove what I prove, then do your own test. Initially, I want to do more tests, but it is actually quite difficult to do it. It's quite difficult because what happened was the space that I have is actually very small, and as I drop the arrow, there is a very high chance that these two actually will hit each other, and they also tend to, because I drop them like that, right? So they tend to catch the air, overcorrect and things like that, and hit the side of the rails, and that can be dangerous. The arrows actually flew off course and things like that. So I have to go up and down a lot of times just to get these 3 videos. So first, it's very tiring going up and down a lot of floors, and it is actually very dangerous because I actually did damage the floor. Yeah, it somehow clashed each other and then it struck something. So I do not want to get scolded. So 3 tests is good enough. 3 of the tests where arrows did not collide and did not hit the rails and things like that. So those are 3 best shots I have. So let me go through the 3 videos I added in. The first test was these 2. Alright, these 2 here. So this is the one with the heaviest point at 340 grains and also the highest front of center. This is the lightest point that I have, 165, and the front of center is the lowest of all the 4. What else? Oh, this is also the heaviest, 47 grams, and this is 34 grams. Then the second test, I put these 2 together. So this one here is 26 grams, this is 24 grams, just very small 2 gram difference. This is a 190 grain point, and this is a 185 grain point, almost similar, but because this one has a heavier shaft, so the front of center is actually quite low, almost similar to this one. So it is quite low, and this one has a very light shaft, so the front of center of this one is actually a lot higher than this one. And then in the last test, I put these 2 together, where 340 grain point and 190 grain point. Both of these are considered high front of center, but the weight difference is significant. This is 47 and this is 24 grams. So you can view the video multiple times. I actually slow the video down to 1/5 the speed so that you can see as precise as possible. If there is any smallest difference, it should show in the video. 1/5 meaning 0.2 seconds per frame. From what I see, there is absolutely no difference, right? Because you see there's 4 arrows, right? So I linked these 2 together in one video, then I do the other one with these 2, and then after that I cross these 2 together, removing this one, these 2 together, and all of them are identical. They hit exactly the same time to the ground. So all of these have different front of center, they all have different weight, but they fall from pretty high up, horizontal starting position, let it fall, and all of them hit the ground exactly the same, meaning that the front of center and the mass of the arrow will not affect the fall time of the arrow. So if they all fall at the same amount of time, then that means given a fixed velocity forward, all of these arrows will travel the same distance because they will only fall for the same amount of time. I hope this video gives you enough proof, and if you are still not satisfied with the result, you will have to do your own proof and in fact scientifically disprove if you think that I'm doing it wrong.